Thank you very much. It's a pleasure to be with you all today. And I understand I have 50 minutes or 1 hour. How much do I have? Something like that. I'm just
going to 50 minutes.
50 minutes. All right. So guys, feel free to jump in and ask questions. I can refer you to an online papers that we have on this if you want to follow up. But I think it's key to kind of appreciate the problem, the challenge I'm going to talk about. So feel free to sort of unmute yourself and ask questions as we go. So the problem I'm going to talk about today is focusing on a bottleneck for machine learning, which is, as you described, specifically for supervised learning, is that one of the major bottlenecks is getting labels, specifically when the labels are actually labels that must be acquired from humans. When we need human intelligence and human judgment to acquire the labels. And there's more and more very important tasks, and I'll go over some of them to describe this, where this is necessary. And what's really cool about this problem is that humans have these properties where they can be very costly, and the other thing is that they bring with them imperfections and even biases. So when you bring all these issues into that framework of machine learning, that gives rise to a lot of really interesting problems. And in general, a lot of my work is really at that human AI integration and collaboration, where humans are kind of integral part. In this case, in the talk I'm going to focus on today, is one where the problem is compiling the data with a limited budget, where the labels are acquired from humans. So most of the work in machine learning is by far really developing the recipes for modeling, right? The model induction sort of processes. How do you generalize from data to produce a particular predictive model? But the data itself, this is the raw material. These are the raw ingredients from which models are made, not just the recipe. While we have this kind of fascination with the algorithms that develop the models themselves, the data is fundamental, because as any recipe, if you don't have the right ingredients, the outcome is not going to be satisfactory. And when we need to acquire data, where we're not in a situation where we have abundant data, where we need to acquire it, for example, in the context that I'm going to focus on today, where humans are necessary to provide those labels, we're running into significant challenges. So many tasks that require human judgment, that includes human labeling of medical images, human labeling of text in order to build predictive models on these images or on these texts, require human intelligence, human judgment for us to acquire the labels. And I'm going to use the term label throughout the talk, basically corresponding to the dependent variable values, right? So we may have tons of images or tons of posts, text posts, but we need humans to tell us whether this particular post has hate speech in it, for example, or whether there is a particular, or whether it's humorous, or whether there is a particular suspicious tumor, for example, in the image. And human are very expensive to acquire, right? I mean, their labels are very expensive to acquire, and their labels are also imperfect. So the opportunity arises with online labor markets, especially when we talk about sort of intuitive tasks for humans that require intuitive tasks for human to label, but also, it's really very at a rudimentary phase, these online labor markets, but really even labeling medical images. I mean, there's no reason why we shouldn't reach out to a radiologist around the world to go and ask them to label different images. So the opportunities with these online labor markets are huge, because for the first time, we have access to these unprecedented immediacy and scope for label acquisition. So, it used to be a major bottleneck. Well, it still is because of the challenges I'm going to talk about today of acquiring, for compiling data sets that require human labels. And these online label markets really present an amazing opportunity. The challenges with those markets are, first of all, is that human labeling by nature are inherently imperfect. So not all of them are going to be accurate. They might even introduce specific biases, which I'm going to talk about later. And cumulatively, of course, they're costly. So for us to exploit and for this opportunity to materialize, for these online label markets opportunities to materialize, we need methods, we need algorithms to tell us, if we have a budget to label a large data set, what do we offer for labelers? How much do we offer for labelers to produce the best possible model as a result from these labelings, given that these labelers can be imperfect? And now I'm going to go into some of the characteristics of these markets and of human labeling that actually matter in this case. So overall, we have these platforms that are awesome, but typically we will be limited to a budget. And it's possible, and that's something that research actually from social science has demonstrated, that if you offer different payments for labelers, you can get different quality of labeling, okay? Which sounds reasonable, right? This is the nature of markets. But it turns out, actually, interestingly enough, that the relationship, and what I'm showing you here, these three plots, are three trade-offs between what we see on the x-axis is the payment that's offered to workers on these online labor markets. And the y-axis is the quality of what they produce. And different experiments, field experiments in these online labor markets found very different trade-offs between payments and the quality of the labels. By the way, these were across different tasks, potentially different times of the day, et cetera. And there's no theory to tell us for a particular task, what I mean task, I refer to like the domain, the actual data. Are you going to be labeling medical images, or are you going to give me labels for image, for layperson sort of labeling for images, or image posts on whether or not they have hate speech on them, or rage speech included on them. The relationship between the pay and the quality they're getting can vary. Sometimes it appears to be completely flat, no matter within a range of payments, you might offer different payments, get no better quality. Sometimes the quality, like the plot I'm showing you in the middle, it might increase if you increase the payment, but then if you past a certain level of payment, the quality actually starts to drop. And in other cases, it's sort of more asymptotic. But all this just to tell you, our work is not about figuring out that relationship necessarily, but just to demonstrate that if we offer different payments, we can get different quality of labels, and the relationship between pay and quality is not necessarily straightforward, and it's definitely not known in advance. For any particular data set or domain that you need to be labeled, and at any given time, in fact, because these are global markets, you might have labelers from one part of the world coming up online in part of the day, and other people showing up from other parts of the world later on in the day, and you might get very different trade-offs. So that's one of the challenges when you decide what payments to offer. The other thing is that the payment that you're offering labelers for labeling our data will also result in a trade-off with the amount of data that you will end up with, right? So we all know that your model can improve if you have a larger training set. But if, for example, you're offering a higher payment to get a higher quality labels, you might end up actually having a smaller data set at the end, given you are constrained by a budget. And it's actually not clear in any given data set that you need to label whether acquiring fewer but higher quality labels, for example, because you have to pay more for them, would be more or less beneficial than paying less and getting just a larger sample size to learn from. And it turns out, and as I'll show you later on, it really, in different contexts, something else would be more cost effective and will allow you to produce better results, right? Sometimes offering lower payments, getting lower quality labels, but acquiring more of these labels would end up being better. And in some cases, it really hurts. So you might want to be very, very conservative and offer sort of higher payments, for example, to get higher quality. So for any given data set, there is no, yeah, go ahead.
Yeah, Maytal, can I ask you a quick question on the previous slides? So
Yeah.
what is the previous slides, if you?
Yeah.
Yeah, so in the middle part of that, the curve, what is the reason why you pay more, the quality actually reduce?
Yeah. So that's a great question. And I was also very curious when I first saw this. So the papers that reported it didn't establish a theory, but they proposed some hypothesis. So to my knowledge, actually, this is up for grab. There is no clear theory about why. And in fact, this pattern has been identified in multiple papers. So not a single paper found that particular pattern. One of the hypotheses they proposed is that once you offer beyond a certain payment, that draws a different cohort of labelers, potentially opportunists who wouldn't normally would be drawn to this task, and that would result in a drop of quality. But that's again one of the hypotheses that they propose. So, but that's an interesting. It's important. It's useful to underscore here is that this just demonstrates that when you offer different payments, you really draw a different crowd to your task potentially, and that really gives rise to different qualities. So in this case, they hypothesized that it might actually result in opportunists being drawn to the task, and people who are not qualified or less qualified who are just spammers, right? They're not going to do that task properly.
There's a question in the chat box asking how is the quality measured? Yeah.
Go ahead, if you can read that to me.
How is the quality measured?
Oh, that's a great question. So the quality that I'll discuss later on is the rate of accuracy of the labeling. So how often do we get the correct label? And later I'll talk about other measures of quality of the labels, but we'll start with the rate of the likelihood that you get a correct label given a particular, if you offer in a particular payment.
In this case, you assume the ground truth is known, right?
So that's a great question. So for our experiments, we have access to the ground truth, but we don't assume that it's available for the algorithms. So we're actually not, we're not necessarily trying to discover that relationship. We're going to actually propose something where for a particular payment, we're trying to project or to assess what would be the impact on model performance directly, right? And as I will show, it's not necessarily that higher payments and even higher quality labels would result in better model, because then you can acquire fewer labels, and sometimes that hurts more than the higher quality of the labels, which is an important trade-off for the algorithm to figure out. That's part of why we need algorithms here, because that what is best to do is not necessarily known. So in our setting, we assume that we don't have access to the ground truth for the label. I mean, that's why we're acquiring the labels from the crowd. We don't know what the ground truth is, but to assess the performance of our algorithm, we will use ground truth that's available in our data.
Okay, thank you.
So, all right, so I'm going to skip that. So problem, the really kind of overarching goal that we're trying to address here is we're going shopping for human labels in these online label markets. And we're going to develop a machine learning algorithm that not only learns from data passively, but also reasons about what payments to offer labelers in order to, well, specifically human labelers, to produce the best, the model with the best predictive performance from the acquired, imperfect acquired labels for a given budget. So let me give you kind of an overview of the setting. So the setting is one, and you ask about ground truth. So the setting is one where in practice, what we have is a huge amount, a huge pool of unlabeled instances, right? So what you see here is a small subset for which, let's say, we already acquired the labels, again, from crowd. So not necessarily the ground truth. The label that we have at any given time are not the ground truth. I mean, some of them may be correct, some of them may not be correct because they're all acquired from imperfect humans. So at any given point, we have a huge pool of unlabeled instances, out of which at any point, we've already acquired a bunch of labels. And then we're going to request labels from the market, at which point we have to decide, what are we going to offer labels? So the payment that we're offering labels, labelers, is going to determine what crowd we're going to draw to our task, and potentially the quality of the labels and the contribution to model performance. And then that payment is going to be offered on the market. We're going to offer that payment for a bunch of instances. So we take a set of instances, not everything we have, a subset of the instances, offer them on the market for a particular payment. In the market, there is some trade-off that we're not aware of at the outset between quality, the payment and the quality of labels that we're going to get. And again, we don't know, for a given quality of labels, we don't know what's the effect going to be on the model performance necessarily. And that's what the algorithm is going to try to figure out. And once those labels are acquired, they are added. So these are the new labels we just acquired. They're added to the pool of labeled data that we have, the labeled training set, from which we're going to learn a model. And that kind of is an iterative process. So the approach, and I'm going to motivate it a little bit more later, but approach is overall kind of the very high level before I will say how exactly it does it. But what the approach is going to be doing is a sequential kind of adaptive selection of payments. In every phase, we're going to dispense a portion of our budget, a small piece of our budget, to buy labels. And at the end, we're going to be going over a sequence of these batches. In each batch, we acquire a set of labels for particular payments, and the payments can change from one batch to the next. So our algorithm is adaptive. It might offer different payments in subsequent batches. And once this payment is offered on the market, we're going to acquire the labels. Given the market conditions, it's going to give rise to particular quality. And the payment that we select also allows for a particular sample size. If we offer a lower payment, we can acquire more labels, higher payment, fewer labels. And at the end, we're going to exhaust our budget. And the key thing is, what to offer. So at the end of that process, we're going to end up with the best model for our budget. So what the policy is going to do, our policy, which we call it adaptive labeling payment policy, is going to determine those payments, right? And what a policy does is it goes straight to the core of the issue. And our policy is going to try to select payments that we estimate will produce for the portion of the budget that we dispense, or the portion of the budget that we spend in each phase. We want to offer the payment that will produce the greatest improvement in model performance, not necessarily in the quality of labels we're going to get, right? Because of what I said before, that sometimes higher quality labels might entail higher payments, a smaller sample, and that may not actually produce the greatest improvement in model performance. Sometimes lower quality labels that for which you pay less but end up with a larger sample, will give you that boost the model will benefit from the most. So what our approach will try to do is to directly gauge, directly estimate the impact of model performance if we were to acquire the next batch of labels for 10 cents versus 50 cents versus $1 per label. Okay, which way is it going to go if we were to offer these different levels of payments? And that is the key. So one kind of comment on this, one might suggest at any given point along the learning curve, so if you acquired a bunch of labels before, why not look at the growth of the improvement in model performance that you've observed in the last time you offered a particular payment. So let's say I'm right here, and I'm asking the question, what if I were to now acquire the next batch of labels for 10 cents each, for 10 cents per label? What would be the improvement that I'm going to observe in model performance if I were to offer that payment? And one of the ideas that people had is you can look at your history and say and ask what was the increase in model performance that we've observed the last time we offered 10 cents per label. And that is actually not something that would be a good strategy because of the learning dynamics. The last time we acquired labels for 10 cents might have been really early on in the learning curve, where every label really made a big difference in performance. But right now we're kind of leveling off, and the marginal benefit from additional label data is not going to be as significant. So going back and looking at improvements that we've observed in the past is not something that is useful for this algorithm because of the learning goal dynamic, because of the learning curve dynamics. So what we're going to try to do is we're going to try to project the marginal improvement in performance if we were to acquire labels at different levels. And our solution is actually to use our history, but in a more clever way than what I proposed earlier. And specifically, and it's actually a very simple idea, instead of trying to project, and projection is very hard, that's the point I wanted to make here and I forgot. Projection is very hard because we don't know the accuracy of our labelers, and we don't know what particular label is going to be assigned to any instance that we might need labeled. And so these projections, there's a lot of uncertainties that we can estimate with a lot of error, and these errors can really be compounded, and it's going to undermine our ability to make these projections. But instead of these projections, projecting forward, the simple idea that we have is that why don't we actually throw away? So actually omit from our current training data labels that we acquired in the past for a particular payment. Let's say labels that we acquired previously for 10 cents per label. If we get rid of a bunch of these labels and then learn a new model from the reduced data set, if you will, the difference in performance that we will observe is a great proxy for the benefit that these payments can offer me at this point on the learning curve. Specifically, if I get rid of these labels that I previously acquired for 10 cents, and actually the model performance improved as a result, or didn't change as a result, which is what's happening here, right? I'm going backward. That means that these labels are actually not productive. They're not going to improve the model performance, because getting rid of them or getting rid of a subset of them only improved my performance or didn't hurt my performance, which means they're not helping. But if I were to now omit labels, training instances I previously labeled for 50 cents per label, it turns out that the model performance drops quite a bit, which means that these labels, whatever quality they have, are actually quite useful, because without them, performance drops substantially. And I can compare the drop that I get for different level of payments. Maybe if I now drop instances that I previously acquired for 20 cents per label, the drop is even more significant, which suggests that those labels are even more beneficial, because without them, the model performance is undermined even more, right? So rather than trying to guess what these labels might be, what their quality might be, it's much easier, and no error compounded in this case, of just removing those labels that I previously acquired for different levels to see how much it hurts or maybe even helps the model, and use that as a proxy to tell me how beneficial those labels are going to be. So all we have to do is really estimate the model before and after dropping labels acquired for different level of payments. So just a kind of a quick summary. So at first, this is kind of the framework that we have. The framework allows us these omission or error reduction, if you will, frameworks, allows us to assess the cost effectiveness of learning from instances labeled with different payments. And it allows us to both take into account the quality of the labels, because the drop that we're observing, or the improvement, if the labels were really bad, for example, quantify both the difference in performance, captured both the quality, it's a result of both the quality of those labels, but also the amount of labels that I can acquire for the fixed budget with different payment levels. So if I have to drop labels that cost 20 cents per dollar and my incremental budget is $1, I can drop and buy only 5 of those, right? But if I'm dropping labels that cost 10 cents, I'm dropping or then will acquire 10 of those. And the drop that I'm observing, the difference in performance I'm observing, is a result of both the quality of the labels and the amount of labels that a particular payment allows me to acquire. So that is, no other framework really allowed us to quantify both of these things very effectively. And of course, the other point that is important to make, it allows me to see the benefit of different payments at that point on the learning curve where I'm at right now, right? So right now, how much labels that would cost 10 cents per minute will help me or hurt me? Because I'm measuring the effect at the point I am on the learning curve. And last but not least, because it is kind of an empirical approach, I'm evaluating performance empirically, I can plug in, I can use this approach for any modeling technique that I care to use, right? It's model agnostic in that sense. It's not tailored for a particular, modeling technique, because I can retrain whatever approach I have with and without those labels that I'm omitting. And as I'll report later, to our knowledge, this framework really leads to kind of state-of-the-art performance as compared to any other alternative. So one of the questions that you guys might think about right now is, fine, but can you actually estimate the performance, this drop that you're describing, correctly? So can you really do this and figure out that some labels, dropping them would actually improve your performance and other labels would decrease, and the degree to which performance would decrease? Can you actually order these different payments correctly, or these performances post emission correctly, given that you only have access to noisy data? So all the data that we have at any given time is noisy. We don't have access to ground truth data. So doesn't that interfere with our ability to actually estimate the correct drop in performance that we're going to observe if we had access to ground truth? And the answer to that is yes. And that's another thing that we show in our paper, is that classification error on noisy data is unbiased in order. So in other words, if the performances can be ordered, they wouldn't be correct in value, but the estimate will be unbiased in order. So the largest drop that we will observe would really lead to the largest drop, even if we had ground truth data, right? So that is a really key sort of result here. And we're going to use cross-validation. And again, cross-validation on noisy data is also nearly unbiased estimator of the true loss. So that allows us to kind of get a decent estimate. Okay, so I'm going to run forward. I'm going to say just a few things of related work because we have other developments that I want to report and a bunch of results. But I'll just mention that in terms of related work, there's a lot of work on buying labels to improve quality of the labels per se. Again, we're not focusing on quality of the labels. We want to get better models for whatever budget we have available. There's a bunch of work on repeated labeling where you acquire multiple labels per instance. Our approach, what we're talking about is really paying different payments for the labels. You can still do this with repeated labeling, but the issue of how many repeated labels, et cetera, this is a completely separate problem. And of course, in online labor markets, there are a lot of mechanisms, incentive mechanism for crowds, et cetera, which is again, is not directly addressing our problem. So, and again, another sort of stream of work in the literature is active learning, which focuses which instances we want to label. So again, what we're focusing is how much to pay labelers, not what instances, specific instances we want them to label, but these things can be combined. We can also use traditional active learning policies to also decide on which specific instances we're going to put on the market. But again, this is kind of a separate problem that can be combined. We can still use these algorithms to choose the specific instances. What we're focusing on is how much to offer labelers. So let me show you some intermediate results and then jump to another sub problem that we have and share how we solve that for this sort of overarching problem. So let's do a bit of numbers and show you some initial results of that approach. So evaluation setting is the same as what I've described before. We're going to give our approach. Our approach is actually going to start with using a very small budget to acquire initial set of labels from the crowd. Again, we never have access to ground truth. And then the policy is we're going to build the first model, and then our policy with this omission approach is going to estimate which payment is going to lead to the greatest drop in performance. And that's the payment that is actually the most beneficial, that it's going to also lead to the greatest improvement in performance. And then after every batch acquisition from the market, and what we're going to do as the market, we're going to simulate different trade-offs that have been reported in actual labor markets. Okay, so we wanted to see how resilient this approach is, whether it's going to provide consistent performance, no matter what trade-offs actually exist in the market. What if no matter what payment you're going to offer, the quality of labels is not going to change? Is our method able to detect that it should offer the lowest payment because quality is never improving with payment? Or when it sees this kind of concave shape where at some point higher payments are actually leading to a drop in quality, and obviously is a waste of our budget. So is the method kind of resilient to these different trade-offs that people reported in the literature? And then after every batch acquisition, we're going to show the model that we build from the labels that we compiled, how the model performed on ground truth test data, right? Independent test data that has the ground truth, right? The algorithm itself is not using ground truth to decide about the payments, but we're going to evaluate how well models built from the data, from the labels we compiled, how well they perform on test data that is correctly labeled, to see how well the model performs. So as I mentioned, we're going to evaluate it using different trade-offs that have been reported in the literature. And our main goal is to see whether we get good performance, better than alternatives, and whether the performance is consistent across different settings. And we're also going to try it with different modeling technique to see whether it's somehow not working for some modeling techniques, to show whether it has that generic property that I suggested before. In terms of data, we're gonna use also different data domains to show whether the data domain itself might have some idiosyncrasies under which our approach might not work, for example, might not lead to reasonable performance. And again, what we're looking for in practice is we want a method that can be relied on, right? So produce somewhat consistent performance. Unfortunately, our approach doesn't really lend itself to closed form sort of analysis, but we're going to show some empirical results that we think are very convincing. And again, since we published the first paper on this, and now I'm going to report sort of another development, we haven't been able to see in the literature and in our experiments anything that does better than that. So in terms of alternatives,
Maytal, there's a question in the chat box.
Yes.
Are you assuming the same rate of payments to all the labelers?
Oh yes, this is a great question. Thank you, Narashima. So or is it ready? What's your name? Sorry, I misread. So the payment, right? So we're talking about markets, and that's a really important question. I don't think I clarified this. We're talking about markets like Amazon Mechanical Turk, where we don't pick the specific labeler that is going to provide, but we're going to offer everyone, correct, the same payments, and the market results in different labels drawn to these different payments, which is why we're getting these trade-offs. However, the same result, the same mechanism can be used if you have certain labelers that request particular payments, right? So if there is a labeler whose quality I don't know at the outset potentially, but say I'm requesting 50 cents per label, and another labeler tells me I'm requesting only 10 cents per label, per label. This mechanism, this algorithm can be used to decide which one of these labelers is going to get the next batch, right? So it's equivalent in that sense. But originally our thinking was on these markets where you offer a payment and then the market give rise to a particular quality. But ultimately the same behaviors can arise if you have distinct labelers, let's say people, doctors, or layperson who are going to label posts for hate speech, etc., who are requiring different payments for their work. So hopefully that clarified the question, but let me know if there's any useful follow-ups. One of the alternatives that we thought about is, for example, what if we always offer the highest payment, for example, and potentially in some cases it can really guarantee that you get sort of high quality of labels. And you can also always offer the lowest payment and then guarantee that you compile the largest sample possible, right, to get the larger training set size. And a third policy is when you are doing some sort of a round robin, or rather uniformly drawing from that different payment levels. So you're not always getting the same payment level, but you have kind of a uniform mix of payments across these different acquisition phases. It turns out that really the highest, offering always the highest payment, if you consider what the trade-offs that have been reported in the literature between quality and payment, if you're always offering the highest payment, that approach can be optimal in some cases, but it can perform miserably. It can be the worst approach in other cases, which is the blue curve here. Similarly, if you're offering the lowest payment, these are not reliable alternatives, because in some cases, these would lead to the worst possible results, and so wouldn't be reliable to be used in practice. But the uniform one, where you just acquiring different payment levels at you're acquiring labels, at different payment levels, that at least is reliable in the sense that it's never going to be performing miserably, right? Because you always have a good representation of the different.
So, Maytal, I have a question for you.
Yeah.
So is the assumption here, you're going to have 100 labels that you need to get done, and I'm going to offer them, let's say 10 of them now for 25 cents each. And I look at the performance of these, and the next batch of 10, I'm going to offer them for 15 cents or, yes, maybe in 40 cents and so on. So the price you're offering is changing. So if I'm a labeler, I'm going to get 25 cents for a batch of 10, and the next batch I may get 40 cents, and next batch I may get 5 cents.
Yeah, again,
okay, so if that is the case, I have a question, which is that then there is likely that the assumption here that quality is independent has to be verified. That is right. If I have a difficult to label image and I'm willing to pay 50 cents to get that labeled, the user's expectation, the next image I'm going to get 50 cents is going to be likely higher. And if you only offer them 5 cents, maybe they're not going to pay as much time to label that. So there is I'm concerned a little bit about here, the independence assumption.
Yeah, so you're concerned about earlier payments levels affecting actually future quality, right, of the label.
Absolutely, or just this noisiness of it's going to be tuning out or tuning in kind of behavior, and the quality is going to change.
Yeah, no, that's a legitimate concern. The way we thought about this, and again, this is something that I guess would be a very interesting kind of follow-up research, is that given these are large markets, especially the ones for human labelers, is that you don't necessarily the same set of a small set of labelers are observing your task, and sort of that changes the quality that you might get from the market. Is the market large enough so these things are not going to affect the quality in the market? But in some setting, it could be a smaller setting or not like a large market, where you have the same people observing those subsequent posts, right, of tasks, where it can affect the performance. And that's a great question, and something that we haven't looked into. So our focus was on these markets where we did assume that.
And even if it's large enough, I think it can affect, because let's say I get paid 50 cents. And I happen to see another payment that's 25 cents in the market. I may not even attempt to get to that, because I am expecting to see another image for 50 cents payment. I may self-select where I'm going to participate.
Yeah. No, I think that's a legitimate concern. We didn't consider this in this paper, and this may be something that would be useful to consider, right? To assume a certain dependent process, certain dependency in those sequences, and look at how you can account for that as well. But that's not something that we considered. The other thing is that I'm now thinking about the other context. So that's something that can arise potentially in a market where you have the same labelers sort of observing your offerings or affecting their willingness to take on a task. And ultimately for us, what matters is that what you're claiming, that it might affect actually the subsequent qualities that we could get for different payments, right?
Yeah, so I'm concerned actually that the curves you're going to draw for one label are going to be dependent on the other payments you made for other label. That's the assumption about that these curves are independent is what I'm questioning.
Yeah, but yeah, so no, that's a legitimate concern. Again, we in this paper we assume that that's not going to affect future labels, and again, to a future quality of labels. And as long as this happens, right, our our policy should work very well. If there is a strong dependency, then you probably need to do something. You probably need to account for that dependency in the process. So yeah, this is a fair question, and something I would probably want to think about to see whether there is something in the literature actually that suggests that, for example. Okay, so the other thing, by the way, I'm thinking about the case where you are acquiring from specific labelers, right? Then it wouldn't change, right? Because then you acquire from one labeler who's requesting 50 cents, you decide to acquire from them. In the next batch, you are free to request labels from a different labeler who is acquiring a different level of labels. But in a market, potentially that could arise. That would be interesting to see if there's any report on this. So let me show you some results, and then I want to talk. Hopefully, I have time. Do I have until 2:50?
Yes. Yeah, 2:50.
2:50. Okay, so I do have 10 more minutes. So let me quickly show you some of the results that we have on this. And again, to our knowledge, there are no other policies. That there was actually policy that was published and we compared with it, but we weren't able to replicate what the results that are reported in the paper. And we did, talk to the email the authors and couldn't get any response. But that method performed even worse than uniform, kind of the round robin one. So we didn't include it in our results. But other than that, the benchmarks that we proposed are the only ones that we're aware of. So what we're seeing here is the cost savings using our approach to achieve the best performance possible with the alternative. All right, so this is kind of the cost difference, the budget saving, the savings in budget that this line represents are the numbers that I'm showing here, right? So what was the cost saving of using our approach relative to the best possible alternative? And what we did is that we experiment with different data sets where usually human intelligence is required for the labeling, and they have different properties. And we also simulated different trade-offs between payment and the quality of the label that can be received. And overall, I don't know that the average here means something, but you can observe the range of savings. The bottom line is that the approach is at least equivalent to the alternative, but very often produces much better models, much better performance than the alternatives for the same budget, right? So it's never kind of the worst approach to choose. So it's either equivalent or produce better results. And I'll show you some diagnostics later on. We also changed the trade-off. So to some degree, that's somewhat related to the previous question. So what we did is we assumed that something happens on the market. We're encountering a particular trade-off. Let's say at some point where you're seeing here concave to asymptotic or fixed to asymptotic. Let's say with fixed is that what you're encountering, or in this case, what you're encountering is that initially there was this concave shape that been reported repeatedly by multiple papers. And the policy works with that market. And then at some point, the trade-off in the market completely changed. And it could be for various reasons. Because these are global markets, it could be that now you're getting people from the different parts of the globe sort of coming online and starting to take on jobs, or there could be that we affected the market, etc. But the market all of a sudden show very different trade-offs. You get now all of a sudden different qualities for different payments. What we find is that because we estimate the effect of recently paid labels, we can gauge the current effect of different labels on the market. On the performance of the model. So our models, the improvements are not as large, they're slightly lower than before, but overall the model is very resilient to these changes because again, it's adaptive and it gauges what happens on the market, right? So while it may not anticipate that change in quality that you're encountering, it can gauge them and it adequately respond with different payments. So one of the things I wanted to tell you about, and hopefully there are two things I wanted to show, is how this payment strategy that the policy produces changes across different settings to achieve good performance for a given budget. And specifically, when, does it sometimes offer higher payments and then produces a smaller samples, a smaller data set? Does it sometimes produce, larger samples, but, pay less and produce a training set of a lower quality? What does it actually do in different settings? So we actually looked into all these, we tried, dozens of different settings, as you could see in the result. So here's a setting where we assume there's a fixed trade-off in the market. Of course, the policy doesn't know that. No matter how much you're offering, the payments, the quality is not going to budge. And this shows you empirically that that's exactly what we're observing. Like that we pay, as we pay more and we offer different payments, the average quality of the labels doesn't change. And what we find in this case, and what we're plotting here on the y-axis, is the number of labels that we acquired and the cost as we acquire more and more labels. So you can see that our policy eventually bought more labels. That's the number of labels, right? Bought more labels, so bottom line, than the alternative policy, which means that it figured out that it can pay less, right? It shows lower payments. And so it was able to compile a larger sample size for lower payments in that particular context, which is really what you should be doing. In another context where we had sort of a relationship where the quality of the labels increase as you pay more, we found that in terms of the quality of the labels, our policy, which is the red one, decreased the quality of the labels. So paid less. And in this case, paying less means that you get lower quality, right? So really the quality of the labels that our policy acquired as compared to the alternative policy, the quality of our labels were lower. And as a result, we ended up buying more labels than the alternative. And we produced, better models as a result. But in a third setting, where, it was more kind of asymptotic, the quality of the labels that our policy acquired were actually higher than the alternative, significantly higher. So as we acquired more, we acquired higher quality labels. And as a result, we acquired fewer labels. So our sample size was lower. Here, the y-axis again is the number of labels we acquired. So we acquired fewer labels for the same budget. We couldn't afford to acquire as much. But again, the policies are different. It's the same algorithm, but it produces very different labeling payment policies to produce better models for a given budget. So it really is very versatile, and it does kind of what you expect it to do. It really gauges what is the cost effectiveness of different payments, and it ends up producing the results that's expected. So we're very pleased to see that kind of responsiveness to the market conditions. So I want to jump ahead because I only have a few minutes left, 3 minutes left. So one of the issues that can arise is not just that the overall quality of the label is lower, no matter what instance the labelers are labeling, but in some cases, human labels also exhibit bias. And specifically by bias, what I mean is that for different instances, for different training examples, their error can be different, okay? So if you're a physician, sometimes diagnosing a respiratory condition would produce higher accuracy than if you have to diagnose depression. And human labelers who label hate speech, and we've seen this and the papers show this, show lower accuracy when they're labeling African-American text than they labeling non-African-American text, for example. So bias for whatever reason, for knowledge reason, gaps in knowledge or prejudice, humans exhibit that bias. And that introduces a problem for the way we estimated the drop in performance, which we fixed. So the drop in performance no longer retains the order when humans exhibit this consistent bias. So what we did, we dug into machine learning theory or learning from noisy labels, and we weighted the loss that we estimate from drop-in instances to account for the bias that we observe in the data. And again, without using ground truth, we estimated the bias using sort of prior literature on how to estimate sort of the confusion matrix for different payments. So every payment can produce different confusion matrix, different levels of errors, bottom line, different levels of error for different kinds of instances. Sometimes the kind depends on the label itself, the true label that we don't, sometimes it depends on a sensitive attribute. Is it a man or a woman? Is it African American language or other or regular American language? And we correct the loss that we estimate empirically from the data. And in this case, we said, well, if we're accounting for bias, maybe we want to measure other performance than accuracy of the models. How about the fairness of the models? What if that matters? And again, because our approach is empirical, we can plug in whatever measure of performance matters for the context. And so we consider both humans who exhibit sort of these consistent biases for different instances, really exhibiting very different rates of errors, and where the goal of model performance is not just accuracy, but things like fairness, et cetera, et cetera. And we also use data sets where you care about these things, like when you try to decide what income someone is going to get, and you use this from historical data, or we use the recidivism data set where you try to predict whether someone will reoffend and whether they should be basically, there are decisions that can be based on these algorithms. And so what you see here is on the y-axis is the unfairness or the bias. So lower values are actually better. And our approach with the corrected, with the weighted loss is this one, where again, the same framework works while we account for the fact that labelers can have this consistent bias. Again, different measure of performance, different type of problems with the human labelers, but the same framework works once we corrected the loss. Here, it's just a different measure of performance where we said we care both about accuracy and about bias. So we want fairness and accuracy. Each kind of has a different weight. So we have sort of a linear trade-off between accuracy and fairness. And what if that is the objective of the organization or the task? Once again, all we have to do is just plug into this framework that we offered. And our approach still is very competent. Both the blue, by the way, is a little bit worse version, kind of a worse variation of our approach, which does okay, but the weighted loss that we produced, that we propose, is actually much, much better. So again, it's very versatile framework that we found can be used for different types of biases and imperfections that humans exhibit in practice, but also can be combined with improving different model objectives that are not necessarily just accuracy, but other things that we might care about in practice. So I think I went over like 2 minutes over time. So thank you very much, guys. I don't think we have time for questions given we only have 50 minutes, but I am happy to answer questions offline, and I'm happy to also give pointer to some of the papers that I reported here.